We are Team Manta Ray.
And our project is using open data tools to give hesitant cyclists the confidence to hit the streets. Alternative transportation plays a crucial role in Virginia's transportation objectives, with bicycling becoming an increasingly popular option. This has led to increased investments in bicycle infrastructure across the Commonwealth, including the development of citywide bike networks. But our bike networks are far from perfect. Many dedicated bike lanes end unexpectedly. In addition, existing bicycle facilities were not all designed to provide the most comfortable riding experience. For many bikers, safety is a much larger factor, not only in their choice of route, but also in their decision to travel by bike at all. If we look at this route in Google Maps, the suggested routes for cars are identical to those suggested for bikes. We want to make a bike route finding tool that incorporates safety data into the route selection. We then want to enrich the resulting route with all openly available information on the route.
Current route finding algorithms rely on network databases that contain every existing segment of road or trail with information about its length, speed limit, and legal directions of travel. A route finding algorithm essentially creates a solution to a route between an origin and a destination by minimizing the cumulative weight of the segments along the route. The weight can be any value, such as distance or time. In this simplification, a route finder would choose the bottom route if the weight is defined as distance, because the sum of all the segments' distance is lower. However, if we add in historical crash data along the route and use them to give a safety penalty for each crash, the algorithm will choose the top route. We built a safer route finder by using OpenStreetMap network data for the city of Richmond. A Python library, OSMNX, applies network algorithms to this data. We enrich the network data with VDOT historical crash data and average annual daily traffic values for each segment of the network. VDOT data provides very detailed location and severity of traffic crashes for the past 9 years. We multiply the distance of each segment by a danger coefficient. For example, the danger coefficient starts at 1 but is increased by 0.1 for each crash along the segment. Each increasingly severe classification, such as minor injury, severe injury, and fatal injury, get an increasing penalty added to the coefficient. Bike-involved crashes get a large penalty. Fatal bike-involved crashes get the highest penalty.
We also use average annual daily traffic for each segment. Empty residential streets 1 or 2 blocks over from major thoroughfares give considerable peace of mind to hesitant bikers. Low traffic values decrease the danger coefficient, while higher ones do the opposite. After the total danger coefficient is calculated, it is multiplied by the distance, and that becomes the value the route finder attempts to minimize when selecting a route solution. To test the effect of the safety coefficient, we randomly select 1,000 pairs of points in Richmond. We run the route finding algorithm on each pair twice, first with only distance as the input, and then once more to find the result using our danger coefficient. You can see here that the distribution of route distance goes up. This is because the safety coefficient sometimes makes the route finder choose longer routes that are safer. But we can see that the distribution of crash incidents passed on each route has decreased as well. This is not surprising, as the algorithm is now directly considering crashes in its choice of route. By assuming that historical crash data is a proxy for dangerous areas, we may infer that the danger coefficients choose safer routes, but a more rigorous experimental design would be required to assert this.
If we look at our prototype of the route results page a user would see, we can see these 2 routes. While the red line is shorter, it has chosen Broad Street, a very busy road. To provide an enriched information environment, we have found the live traffic camera feeds from 511.org that are along this route. By using AI computer vision algorithms, we can also provide a real-time car and bike count for these cameras. This gives the potential biker a preview of the route, allowing them a more informed decision about what to expect along the route in red. The route in blue is our danger coefficient route. While it still is parallel to the red route, it is relocated 1 or 2 blocks over to a much quieter residential street with far fewer crash observations and much lower average annual daily traffic. Future development could include a sensitivity analysis to fine-tune the danger penalties for each type of crash. Additionally, we might explore using real-time bike and car counts to inform the danger weights in real time. We envision a social aspect to the tool as well. Biking in groups is far safer. Programs such as bike buses, where groups of children and families bike to school, could be extended to every commuter who may want to find local bikers to commute together along the same route for increased visibility and confidence.